Hello everyone, welcome back. Let's continue the lecture on stiffness. So, how we can change the stiffness and what is the effect of stiffness on overall performance, that is what we are talking about. So, what we realize that many times very often the stiffness is the main criteria when we are talking about any design. So, although most of the time we spend on failure and we talk about stresses when we do the courses on machine design, but what we realize that when it comes to functioning performance, what we realize that stiffness is the main controlling factor in the design of the part. And as we discussed earlier, so if you see machine tool frames, so we want it to make extremely rigid and so that we can achieve high accuracies. Also, the vibration issues we want to eliminate, and that is why we wanted to have very high stiffness in most of the parts we design. But we also understand that since stiffness is also related to the deflections, what we understand that if these deflections are very high, if there is excessive deflection in any component or any part, what we realize that there can be a lot of interference between the components. At the same time, there can be disengagement as well. So, for instance, if we can think of gear assembly on a shaft, if there is a lot of deflection because of the loading, but we realize that we will have a lot of noise because the gears are either interfering or disengaging, and even it will cause a lot of problem on the bearings. So, it is very important to understand that okay, of course, the stresses are important. We do not want the parts to fail, but at the same time when it comes to the performance while it is working, I think it is very important to take care of the stiffness part. What we also try to learn in this course is when you talk about the stiffness, many times we talk about the springs, and very often what comes to our mind is the helical springs, very usual shapes, or torsional springs, or what we can say leafy springs. So, these are very typical shapes or typical elements what we use in the conventional design. But when we are talking about the stiffnesses, what we realize that any component, any geometry, what we have in the machine, and depending on the loading conditions, what kind of loading it experiences, accordingly there will be deflections and the stiffnesses will be defined accordingly. So, I think it is very important to understand what kind of loading we have and what kind of deflections we are talking about. Of course, we are still talking about these deflections under loading within the elastic range. So, for instance, if we talk about the first part, is a prismatic bar we can say, or any mechanical component, and the loads are in tension. It is a tensile load. So, it is in axial direction. The same member can also undergo under bending load. So, it is supported here and there might be a load acting at the middle. So, it is a different kind of loading, and what we refer to generally is bending load. So, it will deform under bending. If we take this case a bar, and if there is a twisting action. So, there is a torsional load here and trying to twist. So, it will also go under deflection. So, there will be a twist. So, there will be torsional load acting, and accordingly we will define torsional stiffness. We can also have axial loading, but in compression. So, a smaller bar. It can be very thin structure undergoing compression also. So, under tension we may not have a problem, but same longitudinal member, or if we have axial loading, but in compression, and if the cross sections are very small and what we call it slender, and slenderness ratio we might be talking about in design, what we realize that we also face problem with the stability, and we have to also take care of buckling or warping in 2D cases. So, that is something we also need to understand. But here in this lecture, what we try to emphasize, we want to talk about the stiffness and a stiffness for different kind of loading. So, what we have to understand that the same body can be rigid and flexible at the same time. And I think it is very important to understand this part, because many times when we say rigid, we assume that it is rigid in all the directions. If it is flexible, we tend to forget that it might be stiff or rigid in certain directions. So, we always talk about in terms of degrees of freedom or those directions. So, 3 translational directions and 3 rotational directions, and what is the stiffness in different directions. And what we realize that in many cases these individual members, these components, because of the geometry, what we realize that they can be rigid and flexible at the same time. So, for instance, in this case itself, consider 1 and 2. So, in tension it can be very stiff, but at the same time if under bending it can flex easily. Similarly, if we consider this round bar, again what we see that it can be stiff in for any axial direction. So, any load coming in axial direction. So, the axial stiffness, if we talk about, we can see that it will have a very high stiffness, but under bending load or under torsional load it might be limited and it can be flexible. So, for instance, if we take a wire rope, so cables, wire rope, many times these days we also use for transmissions for over long distances, for instance elevators, even surgical instruments like Da Vinci, they have cable transmission. So, they use wire ropes so that all the actuators can be base mounted and you are still able to control the manipulator at the end. So, what is good about this thing is these cables can be very flexible, and flexible in what sense? The torsional stiffness is very small. So, any wire if we take, so torsional stiffness if you are talking about, it is very flexible. Of course, bending also, it can flex very easily, can bend very easily, but if we apply load in tension, what we realize that it is very stiff, and that is the region what we see that the any hoisting application or any crane, any big object we want to move, what we see these wire ropes everywhere, because in one direction, in the axial direction, in tension, they provide very good stiffness, very good rigidity, but at the same time they can be flexible. And during the course, what we understand that if we choose these elements and place these elements properly, we can make very rigid and very stiff design out of it. So, just keep in mind that the stiffness is not just a overall phenomena, but it's limited to how we are applying the load and what are the deformation, associated deformation, and accordingly we will talk about different stiffnesses. So, we will just go back and try to revise some of the things. So, very simple, but may be very important for this course. So, for instance, if you are talking about a stiffness and only talking about axially loaded members. So, it can be a prismatic member or a bar. So, for instance, if we take this element and we apply F, load F. So, here is in compression, but it can be in tension. So, what will be the extension or contraction when it undergoes in tension or compression? And delta, the deflection. So, if it's a if there is a compressive load, yes, there will be contraction, but if there is in tension, there will be extension. What is that deflection? So, you may find it little difficult to remember FL divided by EA. So, E is Young's modulus and A is the area of cross section. So, A the length and this is the area of cross section what we are talking about. Material property is your E, Young's modulus. So, very easy way to remember is just talk about Young's modulus E, and how it's defined is a stress over strain. And when we do that, what we realize the stress is F upon A. So, whatever is the force we are applying and what is the cross sectional area. So, here the cross section area is circular. So, if it's prismatic, it can be square cross section or rectangular cross section. So, that area. So, what we also understand that whenever there is a member loaded in either tension or compression, what we also realize that the whole surface, whole area, that cross section takes the load, and that's why it's a very optimal kind of loading, and that's the region we wanted to have axial loading all the time, or it's a preferred choice. So, the stress is F over A and the strain is delta, that is the deflection. So, it can be compression or it can be contraction or extension, and over the length delta L. And when we rearrange, what we realize that E is now F L divided by delta A, and if we want, we will rewrite what we will realize that delta is function of F L over E A. So, now when we want to talk about a stiffness, this is how it is defined. So, the stiffness is the force, whatever is the force we are applying, and because of that force, what is the deflection, what is the deformation. Again, is within the elastic range, and when we again rewrite, then what we realize that K is the stiffness is E A over L. That's something we have to remember. And what we also realize, yes, this is stiffness K is a function of E, Young's modulus. So, if the material has higher E value, then we get higher stiffness. But when we talk about the geometry, what we realize that the area of cross section larger we have larger stiffness, but when it comes to L, shorter is better in terms of stiffness, longer the stiffness will get reduced. So, again I think very easy to remember, K stiffness of a bar if it is undergoing under tension or compression, the stiffness is given by EA upon L. Similarly, what happens if the member is loaded in torsion? So, here if there is a torque T acting, so torsional load there, and we have this circular bar, so length L and the area of cross section A here, but in general what we will see that is the diameter, and one of the thing will be important is J value, that is the polar moment of inertia. And in this case we can also derive it similarly. So, talking about the modulus of rigidity and the stress over strain in this case, and then if we rearrange we can arrive at the angular deflection. And as we wrote about axial deformations, similarly for rotation also we can just replace with the rotational parameters. So, F will be replaced by T, the torsional load, torque, length, and E value will be replaced by G, the modulus of rigidity, and the A value, the area of cross section, which is important in axial load, but in this case it will be polar moment of inertia J. And later what we realize that there is a modulus defined. So, this J is applicable when this is a circular bar, but if it is a different geometry then it is an empirical relationship, and we can find it many of the design books. But yes, for the time being we can just remember. And if we talk about the torsional of stiffness, so what we are talking about is when we twist, when we apply a torsional load T, what is the associated deflection. So, how this the end rotates, that is theta, right. So, it was when there was no torsional load, it was initially here, but when we applied the load it moved here. So, what is that theta? So, T over theta, that is the torsional stiffness defined, and when we rearrange it's again G j by L. So, modulus rigidity modulus J values, so higher value J, and then it can give higher stiffness. Again L is, if is a long bar, then it will be quite flexible. If it is a short, then it will be a stiff structure. So, this is about torsionally loaded members. What happens in bending? So, if you want to talk about stiffness and talk about bending, I think what we realize that is not so straightforward, because we need to understand what kind of bending loads are there, how is it supported, how the beam is defined, what kind of loading is coming on that, and depending on that we will have a different kind of deflections. So, I think we will go through some examples, simple examples, and it will be clear. So, for instance, most of the time we will be talking about cantilever kind of setup, and if there is load F acting here at the end, there will be associated deflections here. So, usually how we proceed is we try to find bending moment at some sections, bending moment, and that is how is related. M over E I is equal to d2y by dx square. So, that is how is related to the deformations. So, the loading and the deformation, I think this is how we write. So, we start with the bending moment equations, and we integrate, we can find the angular deflections theta, and we integrate further, and then we can deflections at different points. Of course, we have to apply different boundary conditions, and we can find the appropriate integrating constants. So, for instance, in this case, if the load is applied at the end cantilever case, the bending moment is given by F into x minus L, any x and L we are measuring. So, thus the m is a function of x, we put it over there and then integrate, and we can get theta, again function of x, and y. And when we put the boundary conditions for this cantilever, what we realize that the deformations, the deflections y can be given by this formulation f x square over 6 E I under bracket x minus 3 L. And if you want to have the deflection at the point of application of the force at F, then that is the maximum deflection we get. Minus is because yes, it will deflect downwards. So, because of the coordinate system we have chosen that way. So, F L Q by 3 E I. So, that is the deflection at the tip when we apply forces or a point load at the tip. So, if we just take this case and try to write and try to find the stiffness. So, stiffness is F and whatever is the deflection here. So, if we are simply talking about the magnitude, so deflection at the end is given by F L Q by 3 E I, and if we just write the stiffness, which is F over y, rearrange, and what we find is 3 E I by L Q. So, for bending, I think when any member going under bending load, and if you want to talk about the stiffness, be aware of the case, and then we have to find the K accordingly. So, in this case it will be 3 I by L Q. What we find that, okay, of course, we still have the E at the top, the Young's modulus. I we have, that is the area moment, and that is something we need to understand, that is the area moment we are talking about. And for rectangular cross section BDQ by 12 for circular section. So, of course, I think we can always refer to the books, mechanics of material or solid mechanics, and we can update ourselves. So, that area moment is required in this case. So, larger, better. So, if the material is distributed away from the neutral axis, what we realize that I value is larger and larger, and then we can get higher stiffness, and that is the case when we use I beams. So, if the same area and then the material or the area is like away from the neutral axis, then it will be stiffer and stiffer. What we also need to understand, that is the length here is up to the power q is and this is very important, because moment we increase the length is going to be very flexible, and this is one of the reason why if we want to go for compliance, or suppose if you are designing any kind of flexures or compliant mechanisms where large deflection is the requirement, then simply increasing that length can give us a very flexible system. But if you want to have a stiff structure, many times for the same reason is not preferred. Otherwise, we have to put a lot of material. So, I we have to increase somehow and compensate. So, what we realize that k is proportional linearly varying with respect to I, but if you are talking about length is to the power q. So, even a small change in the length will make a huge difference, and I think we have to be very careful when we are trying to design things for stiffness, whether it is for high stiffness or low stiffness. Accordingly, we have to check these parameters. Suppose if we take the same cantilever and then we only apply the bending moment, pure bending moment, if we apply, what happens? So, again we start with the similar approach. We write in terms of m and then theta and y, we integrate and we find these things, and for this case, yes, here is a constant, bending moment is constant over the length. We integrate and we can find theta. So, we can find theta. So, this is the theta we are talking about. So, at the tip, so where we are applying how it will bend. So, there will be angular deflection, and then this is the theta, which is written MBL by EI, and accordingly what we will also find that the tip will also deflect. So, it is not just the angular deformation, but also there is a linear deformation. If you apply the bending moment, it also deflects. So, we have to realize that, and many times when we write in terms of matrices, what we realize that they are also the linear and the angular parameters are related, and that is how we also get off diagonal terms when we write in terms of matrices. So, in this case, suppose if we write and just compare this one with respect to theta. So, the associated deflection here. So, angular deflection will be given by ML by EI, and the rotational stiffness kappa, which is defined as m over theta. So, this is E by L, EI by L. I think again very simple, very easy to remember. So, whenever there is a cantilever and pure bending moment is applied, what happens? What is the rotational stiffness? So, it is simply EI, the flexural rigidity, many times we call it, because it's the combined E and I value together, it gives the flexural rigidity, the rigidity in bending, and that is why it is called flexural rigidity many times. So, over L. So, always remember, if it is a cantilever and pure bending load is applied, bending moment is applied, the rotational stiffness is given by EI by L. So, we may like to summarize here. So, all the cases and frequently used in this course. So, we are not going for very complex formulations, but simple formulation, easy to use, what we might have studied in first and second year of your mechanical engineer, or if you are not from mechanical engineer, you can easily refer to any mechanics book and easy to understand. So, if it's any member in tension or compression, load is applied and there will be associated deflection delta, and this is the stiffness K, P over delta, and area of cross section A E divided by L, overall length. So, what we realize that when we put these values and if we choose the right material, for instance mild steel or stainless steel, these cables, flexible cables, most of the time we use, and for normal application any engineering applications, usually we use steel, and this E is pretty high for that, and most of the cases they say even a small area of cross section can give us a very good stiffness over the length also. So, that is why what we always say that try to design something so that the loading coming on the members are always in axial direction. So, either in compression or tension, and in tension is much better. In compression we have to also look at buckling phenomena, the instability we are talking about. So, otherwise if it is in tension it may not be a problem, and that is the region like one of the area, the tensegrity, that is how it is designed. So, all the tension structures, tension members, they are made of very flexible cables, wires, and all the compressive members, they can be huge blocks. So, but then you can design very good structures. Even these days the exoskeletons are designed based on that, because it takes a very small volume and a lot of space around to put things around, and lot of designs like space deployable structures for moving things without occluding the space. So, it is a very nice. So, tension always preferred, tensile members or axial members, I would say. If it is in torsion, this is what we have, and K prime G by L. K prime actually is J in when it comes to round section, round bars, but for some different sections not symmetric, it will have different values. So, be aware of that, and we can always refer to catalogs or handbooks to get those numbers. So, K prime G divided by L. Yes, bending for different cases will have a different formulation, and we have to check. For simple cases, if we are simply applying bending moment, so associated deflection theta, and this is the rotational stiffness. So, you apply the bending moment, what is the theta is so simply E I by L, relatable to other cases. But what if we are applying a point load at the end, and there will be deflection here in that direction. Accordingly, we can define K, and here it will be 3 E I by L Q. So, this is something to remember or make note of it. So, I just want to highlight here that in axial direction or in torsion, things may be straightforward, and we can just remember those formulas and can refer to. But when it comes to bending, I think I am trying to emphasize here that if it comes to bending, please look at the boundary condition, how is loaded. It can be a cantilever, it can be a fixed end, it can be simply supported, and accordingly these stiffnesses will be different. So, in case of bending, you have to look at the construction and look at the boundary conditions, how they are joined, how they are connected to other parts, or how they are moving, so that we do not make mistakes in calculating the stiffnesses values. Very important parameter here, and we usually do not cover in our curriculum, UG curriculum, or even otherwise. But what we realize that this transmission ratio has a lot of impact on the overall stiffness, and we try to understand with a very simple example. So, what do you mean by transmission? And usually the question we may have, and usually when we are designing or putting the components and trying to assemble, we don't know like where to put the spring. So, we know that some compliance is required, some stiffness is required, but what is the location, where we should put it, and what is the like point of application of force F. So, with respect to that, where this K is placed, and that placement will have a big bearing on the overall stiffness at this point F. So, call it K 1. So, in this case, what is there? So, you have a simple plank here, and suppose you attach a spring at the tip and where you are interested, and you are applying force F and having a stiffness K. So, what will happen? Yes, K is defined. So, of course, K is F over X, that deflection. So, this is the deflection we get, right, and that is the stiffness we experience here as well. So, it will be, so K 1, that is what we are saying, K 1. What happens if we have this thing? So, suppose this is the point of application F. Now, we move to some other locations. What happens if I put this spring here? What will happen? So, whether F, whatever F I am choosing here, and the stiffness here. So, there will be some associated deflection here. What is that deflection? And what we realize that, right, if we want to make the free body diagram, it is like a lever now, because if you take the bar and there will be a spring will try to pull it, right. So, it is F. So, there will be some force F here, which is function of this leverage. So, take balancing, if we just try to balance the moment at this point O, what we realize, this is the length L, and suppose this is length, or this, call it A, and this is B. So, what will be this F now? F prime, call it. So, if we just try to balance, what we realize, F into L is equal to F prime into B, and then F prime is simply F into L by B. So, L by B, that ratio is there, and here since it's like inside, so this L by B will be definitely more than 1. So, this force will be higher, it is going to be higher than F. So, but the spring here, now F prime is acting on this. So, the deflection here will also increase by the same amount, del prime. And what happens when it comes to this point, again there will be leverage, and what happens, the deflection will again getting multiplied. So, what we realize that there is a multiplication, multiplying effect, it is not just linear. And we have one case here. So, suppose we just shift it from here to here. So, in the middle, midsection, at the middle, what happens? So, I think very easy to work out, but we realize that the force, the F prime here is to F, because it is A is basically L and B was L by 2. So, and times F. So, this gives you 2f. So, I will cancel and 2 will go up and we get 2f. But if we apply 2f here to the same spring k, now 2f is applied. What we realize that the deflection here is 2x 2 times, it's already increased. Earlier it was only x. So, you apply x is how defined f by k. Now, same k, now 2f is applied. So, this will be 2x. Now, again go back, and because of the leverage the deflection will be 4x. This is the delta. So, now if we talk about the equivalent stiffness k, which is f over delta. So, f is same, but now delta is 4x, and so k equivalent f by x is k, it's a k, that is how we defined k here. And 4, if here we know that the point of application, the output and in is a L divided by L by 2. So, that ratio is 2, and if we try to write in terms of 2 that ratio, what we find that there is a square term, and that is why we have written here that the equivalent stiffness is k over 2 square. So, you move to the midsection inside, but you lose stiffness, and how? So, square times. So, placing any member or any stiff or compliant member having value k, it will have a lot of effect on the equivalent stiffness, and this is the one example to just to illustrate that. And so, we can write in terms of the transmission ratio also. So, as I said, so if we write transmission ratio as I, which is V out by V in. So, V in is with respect to where we are placing the component, and V out is the point of interest where we are applying the force or where we are like getting the output. So, here and here, or you can. So, here the ratio will be definitely now 2 in this case, and if we try to just generalize, and later we will try to also look at it, and what we see that we can always write that if I is the transmission ratio, the equivalent stiffness will be k over I square. So, huge impact on the stiffness, and this if we know, then we will also try to see in the design, check in the design what. So, just moving the spring can affect the overall performance. So, if that k equivalent is different, all the vibration requirements, your omega 0 values, all will get affected because of that. And if we know this, I think by now we should be able to also appreciate why certain phenomena or certain things happening not expected earlier. Thank you.